A silent race is now underway across the globe. It is a competition that unfolds not in the glare of stadiums or on the public stage, but in laboratories, mines, and boardrooms. This contest is not for oil, nor is it for gold. The prize is a group of 17 invisible elements. These elements are the hidden ingredients powering every piece of technology we rely on. They are the building blocks of our digital age, the unseen force that animates the devices in our hands, our homes, our skies. This quiet pursuit will determine which nations lead the next wave of technological innovation and progress. The stakes are incredibly high. The future of entire industries hangs in the balance. From the smartphones that connect us to the satellites that guide us. The development of clean energy, the advancement of artificial intelligence, the future of global communication all depend on a stable and accessible supply. Without them, the engine of modern progress would slow. This race is about securing the raw materials for tomorrow's world. Understanding this competition is essential for understanding the world of tomorrow. It is a story of geology, chemistry, and economics. It is a narrative that connects deep earth minerals to the highest heights of human achievement. The outcome will shape global power dynamics for decades to come. It will influence everything from national security to the speed of our transition to a sustainable energy future. The quest for these 17 elements is more than just a resource scramble. It is a defining challenge of the 21st century. This silent race has begun to accelerate. As global demand for advanced technology grows, the pressure on the supply of these elements intensifies. Nations around the world are waking up to their strategic importance. They are investing billions in exploration, refining, and research. They are forging new alliances and rethinking old supply chains. The goal is simple: to secure a place at the forefront of the technological revolution. The story of this race is the story of our time, a testament to humanity's unceasing drive to innovate and build a better, more connected future. What are these mysterious elements that hold so much power? They are known as rare earth elements, or REEs. This group includes 17 chemical elements from the periodic table. They are not always rare in the sense of being scarce in the Earth's crust. In fact, some are more abundant than silver or lead. Their name is a historical relic, stemming from the fact that they were difficult to separate from each other when first discovered. Their true value lies not in their scarcity, but in their extraordinary magnetic, catalytic, optical properties. These unique characteristics are what make them indispensable to modern science and engineering. These elements are the secret ingredients that give our technology its magic. A small amount of neodymium can create the most powerful magnets known to man, essential for electric vehicle motors and wind turbines. Terbium and europium cerium is used to polish the precision glass in our camera lenses and microchips. Lanthanum helps create the powerful batteries that store energy for our connected lives. Each of the 17 elements plays a specific critical role that no other material can easily replicate, making them the cornerstones of high-tech manufacturing. The impact of these elements is all around us, even if we cannot see them. They are hidden inside the heart of our most advanced machines. They enable the miniaturization of electronics, allowing for smaller, faster, and more powerful devices. They are crucial for the lasers used in fiber optic communications and medical procedures. In the defense industry, they are vital for guidance systems, drones, and stealth technology. From the hospital to the battlefield, from our homes to the furthest reaches of space, rare earth elements are the unsung heroes of the modern era, quietly making the impossible possible. Ultimately, the global race for these elements is a race for the future itself. Every major technological revolution on the horizon depends on them. The rise of artificial intelligence requires massive data centers powered by efficient hardware. The transition to a green economy is built on wind turbines and electric cars. Our exploration of space relies on sophisticated satellites and rovers. The future of medicine looks to advanced imaging and diagnostic tools. All of these innovations are directly tied to the availability of rare earths. Securing them is not just an industrial goal, it is a foundational step toward building the world of tomorrow. Section 1. From laboratory curiosity to industrial staple. Throughout the first half of the 20th century, rare earth elements were little more than a scientific curiosity, confined mostly to laboratories and niche industrial uses. Their initial applications were modest but clever. Cerium was used to make the flints in lighters. Lanthanum found a role in high-quality camera lenses. However, the world was not yet dependent on them. Steam, steel, early electronics. These technologies did not require the unique magnetic or optical properties that make rare earths so valuable today. They were seen as interesting but peripheral materials, their true potential still locked away, waiting for the right technological key to turn. The turning point began quietly during the Cold War. As military technology advanced, demand grew. Yttrium and garnets, powerful new lasers, samarium alloyed with cobalt, far stronger, heat-resistant magnets. Those innovations moved into missile guidance systems and into radar equipment. The advent of color television created new commercial demand. Europium for red phosphors, yttrium for phosphors too. This was the beginning of the shift from curiosity to necessity. Mountain Pass Mine in California dominated global supply for decades. Refining processes remained complex and expensive. Western companies led R&D, patented uses, and incorporated rare earths into specialized products. Supply chains were simple, centralized, and controlled by the primary consumers. This period laid the essential groundwork for the dependency to come. Each new application, color television in the living room, to the guidance system in a military jet, added another layer of reliance. The industrial ecosystem began designing technologies around rare earth capabilities. Obscure elements on the periodic table were becoming indispensable. The world was not yet fully dependent, but the seeds of that dependence were planted and beginning to sprout across labs and factories. Section 2. The Great Production Shift. The 1980s marked a pivotal moment in the history of rare earth elements, triggering a seismic shift in global production that would reshape the world's industrial landscape. The primary catalyst was not a new discovery, but a combination of economics and environmental concerns. The intricate chemical processes required to separate and refine rare earths from their ores generate significant amounts of toxic and sometimes radioactive waste. As environmental regulations in the United States and other Western nations became more stringent, the cost of managing this waste skyrocketed. This made mining and refining operations, like the one at Mountain Pass, increasingly expensive and less competitive on the global market. Simultaneously, China began to recognize the immense strategic value of its vast rare earth deposits, particularly the massive Bayan Obo mine in Inner Mongolia. The Chinese government made a strategic decision to invest heavily in the industry, viewing it as a cornerstone for future economic and technological development. With lower labor costs and less stringent environmental regulations at the time, Chinese producers could extract and refine rare earths at a fraction of the cost of their Western counterparts. They began to flood the global market with an abundance of low-cost rare earth oxides and metals, fundamentally altering the economic equation for producers everywhere else in the world. The economic pressure was immense and immediate. Facing a deluge of cheaper materials from China, mines and refineries in other parts of the world found it impossible to compete. The Mountain Pass mine in the United States, once the global leader, suspended its operations in the early 2000s. One by one, processing plants in Europe, Japan, and America shut down. The world's expertise in the complex art of separating rare earths began to atrophy outside of China. It was a classic economic decision for countless companies. Why invest in expensive, difficult, and environmentally challenging domestic production when a cheap and plentiful supply was readily available from overseas? This migration of production capacity had profound and lasting consequences. Within 2 decades, the global supply chain was completely redrawn. By the early 21st century, China was not just the world's leading miner of rare earths. It had achieved near-total dominance over the entire value chain, especially the critical midstream stage of separation and refining. The rest of the world had effectively outsourced a strategically vital industry. This created an unprecedented level of global dependence on a single source, a vulnerability that went largely unnoticed by the public as the world entered a new era of explosive technological growth. Today, the modern world runs on a supply chain that is incredibly sophisticated and dangerously fragile. At the heart of that vulnerability is our dependence on rare earth elements. The journey starts deep within the Earth's crust and ends in the high-tech devices we use every day. It begins with mining concentrated in only a handful of countries. Mining is only the first step. The extracted ore is a low-value mix of many minerals. The true choke point is the next stage: separation and refining. This is where dependence is most acute. Separating the 17 rare earths is a masterful feat of hydrometallurgy involving hundreds of chemical stages. That intricate, costly process is dominated by a very small number of facilities worldwide. That concentration creates a severe bottleneck. A disruption at 1 or 2 key plants could send shockwaves through the global tech sector. Even countries with mines often ship raw material overseas for processing. They dig the rock but rely on others to unlock the valuable elements inside. This structure exposes a stark reality. The supply of the building blocks for modern tech is not guaranteed. It is subject to geopolitical tensions, trade policy changes, and logistical disruptions. For manufacturers, from smartphones to electric cars, this is a massive operational risk. They depend on a steady, predictable flow to keep production running. Any interruption can cause manufacturing delays, increase costs, and prevent meeting consumer demand. The global trade web that brings us gadgets sits on a narrow, precarious foundation. This high-stakes dependency defines our interconnected world. We've built a transformative technological ecosystem, but relied on a specialized, geographically concentrated supply chain. The benefits have been enormous: rapid innovation and affordable electronics. But the hidden costs are now clear. The lack of supply diversity is no longer theoretical. It is a tangible, urgent threat to global economic stability and technological progress. Rare earths power the 4 great revolutions of our time: AI, clean energy, aerospace, and advanced medicine. If rare earth supply collapses, entire industries collapse. Diversification is not optional. It is essential. The competition for rare earths is not a conflict between nations. It is the global race for the future of technology, innovation, and human progress. The rare earth war has begun, not a war of weapons, but a war of innovation.